Hello everyone, we are Project 21091 Energy Recovery from Food Waste. I am Abdurrahman and my colleagues Omar, Muad and Jimmy will be presented today. Let's talk about our problem. We have 1.3 billion tons of food waste globally every year, but when it comes to the US, about 14 million tons of food that's discarded every year. But specifically in 2018, we have about 103 million tons of food waste was generated according to the Environmental Protection Agency. So we have a problem. And the best solution for that is to take it and turn it to energy. After a lot of research, we found the best solution is two-phase anaerobic digestion. And by doing that, we're going to process about 10.4 tons of food waste every day, and we're going to reduce the gas emission in the landfills, which contribute to the global warming. And at the end, in our product, we're going to have more than 60% of methane, which can be used as fuel in many applications.
Okay, what we have here is the first part, the PFD, and an overview of the process. The process starts with food waste being transported into the plant, and it will be stored in a designated storage tank. Then through stream two, food waste will be transported to a hammer mill to be crushed in preparation for the separation process, where degradable and non-degradable waste will be split up. This can be done through a process unit that has a camera sensor and an air jet and a conveyor belt. Now, once we have two separate food waste tanks, the second tank, or the degradable food waste tank, will be mixed with water and pumped to a decanter centrifuge, where components of the degradable waste will be separated based on their densities. Hence, fats and oils will be stored in one tank, while protein and carbohydrates will be transported to the next part of the process.
So now we will start exploring part 2 of our process. In this section, we will start with a mixer, as you can see. After finishing the separation process, carbs and proteins will go to a mixer. The mixing process helps break out all of the food waste to ease the process for the upcoming reactor. After that, the food waste goes to a pump and get pumped to the first reactor in our process, which is R101. This reactor is the pre-acidification reactor. In here, a hydrolysis reaction happens. Basically, in a hydrolysis reaction, water is used to break down the bonds in different substances. So in this process, carbs and proteins are being broken to become monomers. This will help the acidification reaction happen in the next reactor. Also, we have a gas meter just to make sure that everything is going well in the reactor. After the reaction, as you can see, stream 16 goes directly into a buffer tank, in which it continues to be mixed. However, stream 13 goes through a pump and a pH controller just to make sure that it is at our desired pH level, which is 6.5. The buffer tank also has a pH controller just for emergencies. After that, our mixer in stream 20 flows through a pump and into the second reactor. In this reactor, 3 different reactions happen, which are acidogenesis, acetogenesis, and methanogenesis. During the acidogenesis reaction, monomers are converted into volatile fatty acids, whereas in the acetogenesis, the volatile fatty acids turn into acetic acid, hydrogen, and carbon dioxide. Finally, in the methanogenesis reaction, methane gas will be produced. After methane is produced, 2 paths will be taken. Methane and CO2 will flow through stream 23, whereas the liquid waste will flow through stream 22 to a storage tank out of the system. Now stream 23 will flow through a refrigerator to cool it down. After that, it will go through an air compressor to be compressed and become liquid. And finally, it will go through stream 25 to a storage tank, and it will be ready for use.
Okay, now we move on to the environmental impact of the process. As we all know, electric power leads to a significant increase in greenhouse emissions through the combustion of fossil fuels. That's why waste energy plants have innovative methods in converting food waste into power that we all can use safely. It can break down organic matters into renewable energy, which is a sustainable solution for a green environment. So now the social impact of the process. Waste energy process can improve the well-being of humans. As we can see, the process ensures a greener future for people since it reduces pollutants while freeing the world from excess food waste.
So after finishing designing our project and determining the feedstock, we believe the cost of manufacture is going to be 18.4 million and the total production cost is going to be 19.6 million. So when it comes to the capital cost, we believe that the total permanent investment cost is going to be 25.9 million and the working capital is going to be 1.6 million. So the total capital investment is going to be 27.5 million.
We're talking about the result, and then we actually started with 20,000 kilogram per day of food waste, but we only use 15,620 kilogram per day. With that, we mixed it with 164,000 kilogram per day of water. From that, we obtained 6,167 fat, oil, grease that was extracted, and then we ended up with a methane production of 29,258 kilogram per day. From that process, we obtained 3.4% of food, fat, oil, and grease extracted. We had 96.6 food waste plus water. And then the most important value here is 84.5 fat, oil, and grease in stream 9, because it's actually the amount that actually help us maximize our process. And then this one actually help with the conclusion where we actually analyze the result, and then we realize that our goal were optimized. How did we know that? By reducing the CO2 emission, which actually had a positive impact in the society by reducing the pollution rate on the landfill. The revenue obtained from the methane will be reinvested in the plant so that we could have more jobs for the people in our community. The thing that we have to focus on next will be the efficiency of the separation process, which will then improve the methane yield and boost our company revenue. This ends the presentation here, and this is our references. Thank you.